Good afternoon, everybody. We're going to go ahead and get started. First of all, can you hear me? Okay, great. Before we begin the presentation, do any ocean studies faculty have any announcements? Professor Cleveland.
Could all of the OS001 students come find me so that I can check you off for attendance after class? Because I didn't get here in time.
Okay, any other announcements? Okay. Well, I have the pleasure and honor of introducing our speaker today. So, our speaker is Dr. Sean Birkel. He is assistant professor at the University of Maine with a joint appointment in the Climate Change Institute and Cooperative Extension. He is also the Maine State climatologist, which is pretty awesome. Sean's research utilizes climate modeling and data visualization to better understand Earth's climate variability and changes across many timescales. He's also the developer of the widely used website climatereanalyzer.org. As state climatologist, Sean works with academic and government partners to provide climate information to Maine stakeholders and to facilitate decision making. Sean's also serving on the scientific and technical subcommittee of the Maine State Climate Council, and I think he's going to tell us a little bit about that today too. So we're really looking forward to this talk, and we'll do questions at the end. So when you're ready.
Well, thank you, Sarah. It's wonderful to be here today. Thank you all for coming, and I really appreciate the invitation. Let's see. Great. Okay, so for a brief outline, I want to share with you a little bit about, I'll start with the description of my background, a little bit more information about what I do as a state climatologist, and also my pathway, how I came to be in this particular career that I am in. And then we'll go over a few slides, Climate Change 101, just so that we all have some baseline information as we then proceed to talk about climate change in Maine. What is the historical record? What have we observed in recent decades? And then also talk a little bit about impacts, and then conclude with adaptation and mitigation and what the Maine Climate Council is doing. I also just wanted to note the Climate Change Institute, which is where I got my graduate degrees with CCI. And CCI recently celebrated its 50th year as an interdisciplinary research institute studying climate, and it's one of the first, if not the first, institute of its kind studying climate. And as you can see from this list, we have a number of different programs, and CCI has a master's program for anyone who is interested in climate as it relates to a variety of different fields, from archaeology to atmospheric chemistry, climate modeling, marine science, and many other things. And as Sarah mentioned in my introduction, I have a joint appointment between the Climate Change Institute and also Cooperative Extension. And so I have, my work has two roles. That is as a climate scientist who does research. My research areas are primarily in climate variability and over a broad range of timescales, from paleoclimate and also, of course, modern climate and future climate. And as state climatologist, however, I focus on data dissemination, helping groups who need data for either research projects or guidance documents. I help them find the data that they need, help processing that, and also I help facilitate decision making using climate and weather information. And so that falls under the umbrella of climate services, and that's a big part of what I do for Cooperative Extension. And Cooperative Extension is a program that, a big part of that is working with agricultural stakeholders and natural resource stakeholders across the state. and there are many needs for climate and weather information in that regard as well. And Sarah mentioned my website, climatereanalyzer.org. I started developing that about 10 years ago, and it's a site where people can go to get climate and weather data sets and models, as well as weather forecasts. So it has a lot of data sets of a similar theme with consistent user interfaces, consistent graphics. It can be used for research, for education, and there are also pages on the site that are for the general public. And then for Maine-specific data needs, I've developed the Maine Climate Office website. And this is just a sample page showing temperature observations and precipitation observations for Portland. But there are 30 long-term sites with daily data that I have easy access to on the site, as well as long-term records on monthly, seasonal, and annual time scale going back to the late 1800s, and other resources as well. And I just wanted to mention 2 recent reports. If you're interested in learning a lot of the details about Maine's climate in a digestible form, Maine's Climate Future 2020 is a report that we published, the Climate Change Institute, Maine Sea Grant through the university, just a couple of years ago, and that is meant to be an overview that's very readable for the public and educational audiences, and gives you the picture of how climate is changing in Maine. And then soon after that, I was involved in a portion of the scientific assessment of climate change in Maine. This is a product of the Maine Climate Council Scientific and Technical Subcommittee. And this goes into even more detail. Both of these documents are available online, and I just wanted to make everyone aware of them. Okay, so now just a couple minutes on my pathway, how I became a scientist and how I came to be here in front of you today. The pathway was a bit winding. I wasn't always certain. And when talking with students, I do like to highlight that I think just about all of us we're never always certain as to the next step, but things tend to fall into place, and that certainly seems to be how it was for me. I originally wanted to go into physics, become an astronomer, and I soon realized there's a little more math than I wanted to have in my life. And I took a year off from college after 2 weeks just finding I'm an average math student, and I think you need to be above average to become an astronomer. I re-entered the program, this was at the University of Maine, as a geology major, because I've always been fascinated by the concept of deep time, and that's one of the overlaps between astronomy and earth sciences is deep time. And I really enjoyed it. I really got drawn into earth sciences on field trips, going out into the field and seeing the different types of rocks, learning about how rocks form in continent collisions, and learning about the geologic history of Maine. And to fast forward, I decided to go into graduate school, also at the University of Maine. I wasn't expecting to stay at UMaine for all this time, but it worked out that way, and I've been quite happy. I had the opportunity to go to Antarctica for a field season as a graduate student in December through February of 2002, 2003, and this is me 20 years ago. And also some field experience studying past extent of glaciers in the western U.S. And then since then, my work has focused on Maine climatology, understanding climate variability that impacts the North Atlantic in Maine, and of course, my duties as a state climatologist. So now, Climate Change 101. There's a quiz after this, by the way. Most, if not all of you, are well aware of the greenhouse effect and how the climate change that we're talking about today relates to the the emissions of greenhouse gases from human activity. And so just as a refresher, the greenhouse effect that we're talking about, and it's impacting the climate in that when carbon dioxide and methane is emitted and the concentration of those gases is increased in the atmosphere, that provides something like a blanket that traps heat within the atmosphere and it effectively prevents the planet from cooling off. It prevents the escape of heat. And so with a higher concentration of greenhouse gases in the atmosphere, there's the cool off, say at nighttime, for example, is less efficient. Now, it gets a little more complex because there's a net loss of heat at the polar regions versus a net incoming of heat in the lower latitudes. But one key point is that the heat, well, shortwave radiation coming in from the sun mostly passes through the atmosphere, interacts with the Earth's surface, including the oceans. Some of that gets absorbed, but then long wavelengths get reflected back through the atmosphere, and that's where those long wavelengths can be captured by greenhouse gases and then re-radiated back to the surface, where it then gets absorbed by the oceans, by the land surface, where it can melt snow and ice. And now the Earth's climate it's a delicate balance through time. If we look at the paleoclimate record, we see that there are these oscillations from either cold temperatures to warm temperatures. And this is over a 400,000-year time scale. This is from an ice core in East Antarctica. Ice cores are known as proxy records. We can recover a deep ice core going down a couple thousand meters and then analyze those ice cores, analyze the chemistry, analyze air that's trapped in bubbles within the ice that captures the climate conditions and also even the temperature at which the snow originally fell and then eventually turned to ice through compaction. And by running analyses on an isotope of hydrogen called deuterium, this is a proxy for temperature. And then here, these are measurements of carbon dioxide, again, trapped in air bubbles within the ice. And we see that this record goes back 400,000 years, but we have other records that go back beyond that, even 800,000 years. But we see this quasi-cyclical cycle of ice ages. That's natural variability over very long time scales. And what is, of course, very troubling in this graph here is that the CO2, since the Industrial Revolution, the concentrations in terms of parts per million has gone well above anything in what we know of the paleoclimate record. And we know that there's a strong relationship between Earth's average temperature and the concentration of CO2 in the atmosphere. And to point out, 400 parts per million was reached about 2015, and now in 2022, we're just under 420, and projected to go to 500 or beyond, depending on greenhouse gas emissions trajectories, the choices that we make, the choices that the global society makes. And let's see. Now, I mentioned that the ocean warming is a key part of this because the majority of the excess heat is being stored in the upper layers of the world's oceans, where it stays for a very long time, and where it interacts with the atmosphere. The warmer the oceans are, the more evaporation there is, the more moisture that gets entrained in the atmosphere. Well, water vapor is a greenhouse gas too, a very important one, and that's part of the warming story. Really, climate change is a story of feedbacks, that when there's a perturbation to the system, such as an increase in CO2 and methane, that perturbation can be amplified by other parts of the system to exacerbate the problem. And this, by the way, is also how ice ages develop, but that's another talk altogether. So a key part of the story is an intensification of the hydrologic cycle. That's the cycle of moisture going from the world's oceans, evaporating, getting entrained to the atmosphere under the right conditions, forming clouds and precipitating as rain or snow. Some of that falls on land. Some of that water will fall over the ocean. But it's this cycle that the warmer the climate, the more intense this hydrological cycle is. It's kind of like if you boil water, turn up the heat, the water will heat up more quickly, and the convection within will become more vigorous. I mention this because part of the changing climate that we are now documenting more and more are extreme events. A tendency towards more intense heat waves, and in some isolated cases, sometimes even intense cold waves that are pretty short-lived, but also heavy rainfall. That's becoming a major problem. Rainfall 2 inches, 3 inches in a day, in some cases in just a few hours, which can cause erosion, flooding, infrastructure damage, but it relates to the intensification of the hydrologic cycle. Now there's also Arctic amplification that links to, as I mentioned, these feedbacks. As the climate warms, the polar regions are warming, and the seasonal extent of snow and sea ice shrinks a little bit, which allows for more heat to be absorbed, which then further melts snow and ice, which then leads to more warming, and it becomes a positive feedback. And I'll show another slide showing change in temperature, but the loss in sea ice is a major part of this. And this slide on the left shows the end of the melt season in the Arctic that occurred in the first part of September 1980, September 10th. The sea ice concentration and extent as measured by satellites. And then in 2016 as an example. Since the early 1980s, there's been about a 50% decline in the average area of ice cover at the end of the melt season. And there's been a change in the winter season as well, but it's most dramatic in the summer. And many people may have noticed that it seems like the fall season, or that summer seems to extend a week or two longer into the fall than it did 20 years ago or so, 30 years ago. And that links up to loss of sea ice and a warming of the northern hemisphere that tends to be weighted towards the end of summer and into the fall season. And there's also a delayed onset of the Arctic winter as a consequence of this. And so this slide here shows the average winter temperatures across the Arctic. So this is December through February average, 1951 to 1980, so a 30-year climatology. And then in comparison to the last 20 years. And it's, as you can see, these shades of red, and you see much of the northern hemisphere here. Most of the warming is over the Arctic. That's where this Arctic amplification is taking place, but it's impacting the entire hemisphere because of atmospheric circulation and because of movement of air masses. And so Maine's winter, for example, winter is getting warmer in large part because the Arctic is getting warmer, and the air masses coming down from the Arctic tend to not be as cold as they used to be. And just another couple slides before we start talking about specific Maine climate impacts. I just wanted to say something about the models that we use to project climate. So when you hear about climate projections, these are coming from numerical models that solve equations of the fluid motion and heat transfer within the atmosphere and within the oceans. And they operate fundamentally like a weather forecast model does. These models have been in development for decades. The physics is very well known. I mean, there's always room for improvement, and there are groups trying to refine the physical implementations, but effectively, a climate model that is used to project out 100 years, it has its own weather within the solution. And it integrates these equations on the second or minute time scale. And although in this slide here, I'm showing a weather forecast, just cycling through hourly time steps for a few days. This is actually what a climate model does, except for it does that for 100 years. And the way they can be used is, unlike a weather forecast model that's, well, actually similar to a weather forecast model, the initial conditions are based on real-world observations, and the model itself has it's tuned to produce, I shouldn't say tuned to produce, but the equations they reproduce Earth's climate, but it's informed by real observations, and it then can show where the jet stream is, and realistic depiction of temperature through the atmosphere. A climate model is initialized at the very beginning of the simulation, and this includes the land surface properties, where there should be sea ice, boundary conditions for ocean temperature, and then the model it will then solve the equations and reproduce weather for year after year after year after year, but it can be perturbed. To use that word again, perturbation. The climate can be impacted by changing the radiative forcing. So for example, the greenhouse gas concentration in the atmosphere can be increased in a climate model such that there is this energy imbalance. And so the weather that is calculated is then becoming modified by this energy imbalance that's affected by, so for example, increase in greenhouse gas concentration. Now, in this panel here, I realize it may be difficult to see in the back, but the green bars there indicate the radiative forcing in watts per meter squared. This is 0, 1, 2, 3 watts per meter squared. And then the time axis, this is the late 1800s, 1881 to 1900, all the way to 2001 to 2012. And so this is showing the estimated radiative forcing of greenhouse gases in green, that's from human emissions. Aerosols, or dust, that's emitted by human activity, and that's shown in blue. And then also solar variability and volcanic aerosols that impacts that provides a radiative forcing. And now this black dashed line here, that's the average of the natural radiative forcings and of the human radiative forcings from greenhouse gases, change in land use, and so on. And as we can see, that this dashed line starts to trend upward pretty steeply after about the 1930s through the 1960s. Now my next slide. I want to introduce, is it still working?
Oh, uh-oh.
Yeah, the light turned red.
Ooh, the right turn red.
Yeah, okay. Well, I'll continue. I want to mention climate models because I want to show this figure. I think it's an important figure. It shows two simulation sets that
Battery emergency.
Look when we started.
Well, in short, these two signals, there's an experiment in which the climate model is subjected to natural radiative forcings only, and that's the simulation in blue. Okay, yep, great. For those online, my apologies. We had to swap out batteries. Okay, so I'll just reiterate what I said just for anyone who's listening online. This panel here shows the results from two sets of climate model simulations. In blue is a simulation that is used for radiative forcings only for natural known changes, from volcanic eruptions and from solar variability. And the simulations in red those simulations include natural plus the anthropogenic, or the human radiative forcings. And then the black line, that's the observed global mean temperature. So these are global mean temperature signals. And as we can see, it's between about 1930 and 1960s that the signals begin to depart. And so this gives us confidence that it's in the last few decades that, as I note here, natural forcings cannot account for the observed warming since at least 1960. And simulations such as this really demonstrate that quite strongly. So now we get into climate change in Maine. We'll review Maine's climate record for temperature and precipitation, and then discuss what we're observing in terms of impacts, and then what we expect in the future. This figure here shows the average statewide mean annual temperature since 1895. This is from, these data are from NOAA, collected from observation stations across the state that have been available for the past several decades. And it shows that there's been a warming of about 3 degrees Fahrenheit on a mean annual, overall on a linear trend. Now you can see that there's significant year-to-year variability, as well as you might be able to pick out there's some low frequency variability in there as well. So decade scale variability. But there's an overall upward trend. And this interval here, in Maine, particularly since the 1980s, we've seen considerable warming across the state. And just for a visual, here's the mean annual temperature across the state. I realize that you can't see the temperature values very well, but the lighter shades are warmer temperatures, and the darker shades of green are cooler temperatures. And so you can see from 1904, which was the coldest year on record since 1895, to 1966, which was pretty much mid-range, and then 2010, which remains the warmest year on record. There's this progression, and so there's this northward creep of heat. The Maine's climate is warming, and this is how it looks on a map. And Maine's climate is getting wetter overall, despite that we may from time to time see impactful droughts such as in 2020. On an annual basis, in terms of total accumulated precip, there's an upward trend of about 6 inches over the past century. And this decade, from about 2005 to 2014, was the wettest decade on record, largely from contribution from the summer season. And there's interesting Arctic connection to that. Now, in relation to this, there's also a tendency towards more precipitation being delivered in heavy or extreme rainfall events. And it's uncertain, but there's evidence to suggest that in the future we might see, although more rainfall on average overall in a given year, the distribution could be that the rain will be, more will fall in large heavy events, but there could be intervals of dryness or drought that are impactful, especially to agriculture and for water resource managers.
Can you just clarify the numbers? Is it an addition of 6 inches over what, like total mean rainfall has increased by 6 inches per year?
Yes,
Between those times?
for rainfall that accumulates over the course of a full year, since 1895 on this linear trend, there's now 6 inches more than there was a century ago. Oh, you're welcome. And of course, if we were to look at individual seasons, we'd see most of that signals from summertime, but it does depart a little bit depending on the season. Okay, so now, in looking into the future, again, using climate models that can simulate the climate system response at the weather scale to various emissions of greenhouse gas increases. So a high emission scenario suggests that Maine's climate could warm by up to 10 degrees Fahrenheit on average annually by 2100, versus the best case scenario in which the warming levels off. And one could argue which is the more plausible scenario. It depends on global action. Depends on what we do here at home in the U.S. and then worldwide. And so there's a wide spread of outcomes that for Maine ranges between 2 degrees warming and 10 degrees warming in Fahrenheit by 2100. And now if we consider the Gulf of Maine, the sea surface temperature warming, that's estimated to range anywhere from 1 degree Fahrenheit to 6 degrees Fahrenheit by 2100. Again, in relation to the greenhouse gas emissions trajectory that society takes. And also in the Gulf of Maine, there's considerable year-to-year variability, and also there was a warm decade in the 50s, and then a cooling after that, but then the warmest past 20 years have been the warmest on record. And I'm sure you've heard about marine heat waves that are starting to impact the marine ecology of the Gulf of Maine and fisheries. And those have been especially prevalent since 2010 and 2012. 2012 was the first really big marine heat wave that we experienced. Now, I really want to mention this. We're here in Castine. Several years ago, I found a couple stories about Penobscot Bay freezing over, and people being able to walk out to islands, and I thought that was really interesting. So I started doing some searching through historical documents and newspapers, and I found that there's quite a wealth of information about how in the early 1900s and at times in the 1800s, it's documented that the Penobscot Bay could freeze over to pretty significant extent. And so this map, I'll describe the photograph in a moment. So here, of course, is Penobscot Bay, and Brooksville, Belfast. And, I've put dashed lines where, from the reading that I've done, from the historical evidence that I've found, was the likely extent of the ice during some of these winters in which the ice was really extensive. I put question marks because I'm not entirely certain, but I probably some of you, actually Sarah mentioned that she's heard stories of people walking over to Islesboro from the mainland. And there are stories of people walking to the Cranberry Islands across Great Harbor off MDI. And I heard from a gentleman a couple of years ago who he had just retired as a ship captain, and he said that in his youth he spoke to a gentleman who was a ferry boat captain who worked off Stonington, and who recalled in the winter of 1934, so this would have been February 1934, he could walk to Isle of Ho over the ice. And then, of course, there are photographs such as this one. This is from the winter of 1904-05, and this is off Belfast. And even going to our south, Boston Harbor at times would freeze over. Even Long Island Sound would freeze over. Chesapeake Bay during some of these really cold winters that we no longer experience. And this term ice embargoes was something that was really common in the literature, at least until 1934. And now this story in particular, because it's very close to home for you folks here in Castine, in February 1918, the Bangor Daily published an article, and I found this on an antique car website. And I found that website just from searching climate information, and this came up in the list, and lo and behold, there was a gentleman who he'd gotten photographs of a Ford Pathfinder, and the gentleman who used to own the Pathfinder told him about the story about how that car had been driven across the ice from from Brooksville to Belfast. And so I'll just read this, a couple parts of this. Automobiling across the bay from Brooksville and the Castine has come to be a regular thing now. The Pathfinder Ford, which made history Friday by being the first car to cross the bay on the ice, made 4 trips Sunday to Brooksville, towing a horse sled loaded with over a ton of grain and provisions, and making the 12 miles across in about 25 minutes. And now this was 1918. It was during World War I. And the backstory is that although it became something of a joyride, because I guess other people joined in, originally it was for a specific purpose. It was to get supplies for the town, because they ordinarily would get supplies from Belfast. So I guess a ship would, Belfast would have the stocks, and then by ship the stocks would be transported across the bay. But in that year, the ice was so severe that for some weeks they were unable to get provisions. And so this trip was made out of necessity, really. But and in another paragraph that I don't have here, the ice was checked along the way because Captain Albert Gray was nervous at first. As I recall, I think the ice was about 5 inches thick. And so, but the last time the bay froze over to this extent, in which the ice edge could get down to about as far south as Rockland, that was February of 1934. Okay, so now, in the interest of time, we'll move on to talking about some climate impacts. And there might be another picture of the winter temperatures in which you can pick out the individual years in which the bay froze over. It shows up in the temperature record beautifully. It's wonderful when historical documents can match right up with climate observations. Okay, so one of the impacts of a warming climate, and I think that this is, to me, an easier way to visualize on a graph how the warming climate can impact ecosystems and agriculture and wildlife. The warming climate changes the relative length of the warm season versus the cold season. And so what this figure here shows is monthly values for the average temperature annual cycle for 3 periods. In the blue line, that represents the average of 1895 to 1914. And then the brown line in the middle represents a century later, 1995 to 2014. And then projected to 2050 in the red line. And it shows that overall, over the past century, there's been just about a 2-week relative lengthening of the warm season and therefore a shortening of the winter season. And so the shortening of the season of snow and ice. And and then this dashed line here, that's for 32 degrees Fahrenheit. Usually it's middle of March when the average daily temperature gets above freezing and snow starts to melt and spring comes. But you can see that it's this change on either side, and note that it's on the later in the years where most of the change in the season length is occurring, again in late summer and into fall. And so by 2050, where the climate model projections suggest that we'll see an additional 2-week change in the relative length of the season. And this, of course, has implications for agriculture, because the growing season is getting longer overall, which in many ways can be a benefit to some crops. But yet, there's still variability. And I think this chart here shows that nicely. This is it's Maine's Climate Future 2020 update. It's estimated from an average of stations across the state going back to 1950. And then this is 2020 on the right. And so this is showing the length of the growing season in days. And I apologize if you can't see those numbers, but it ranges from 120 days up to 170 at the top. And so overall, you see a strong trend towards the growing season is getting longer. But note this dip right there, that's 2018. The growing season is identified by frost dates. So the last frost in the spring to the first frost in the fall. And so one of the caveats, although, say for some crops, it might actually be beneficial. Many farmers find it a great benefit to have a longer growing season. But there's still variability, and one of the caveats is if we plan for having a longer growing season, it could still be a killing frost that comes at what would appear to be a more usual date historically. And longer summers and shorter winters are also, they impact pests and vector-borne disease as well. And I think one of the most notable examples of that is the spread of the black-legged tick, or also called the deer tick, across the state. These maps show the, based on work that's been done by others on the larval emergence of the black-legged tick, requires a certain accumulation of degree days over the summertime. And if there isn't a certain amount of heat, then the tick can't complete its life cycle. But long story short, this map shows in areas with warm tones where the black-legged tick can complete its life cycle and can become entrenched, versus the areas in cool tones where it's still a little too cold for the tick to survive. And so these are the conditions for the 1980 to 89, then more recently 2010 to 2016, and then projected mid-century. And so this is an indicator that the black-legged tick can indeed now spread across the state and will eventually become more entrenched in the northern part of the state, as it is now here along the coast. Extreme weather. Now, we all know that there are, in the historical record, we can find major hurricanes, we can find major heat waves, and intense storm rainfall events. But what we're seeing now is that the frequency is increasing and the intensity as well. And that's in relation to the intensification of the hydrologic cycle. And so as this map here shows, the Northeast region in particular has seen the largest increase in these heavy precipitation events of anywhere in the country. And in Maine's Climate Future 2020, we studied precipitation records across Maine and found that the last 10 to 15 years has had the highest occurrence of 2-inch, 3-inch, and 4-inch per day rainfall for records going back several decades. And it's just to highlight a couple recent extreme events, starting with the remnants of Hurricane Ida, which had huge impacts on the Gulf Coast. By the time it reached the Northeast, it was then an extratropical storm. But there was rainfall in parts of New York and New Jersey, 8 inches, and particularly along Long Island and northern New Jersey. That storm didn't have big impacts in Maine, but certainly caused major flooding where it happened to pass by. Now this figure on the left, I have it labeled anonymous. The person gave me permission to use this, but it's someone's property. It's their farm in New Hampshire that last July there was a major rainstorm that I think it was about 5 inches fell within a few hours. And this is alongside a river, and this massive amount of erosion took place from that one rainstorm that was just associated with the thunderstorm. What embedded within it was a cell that produced a lot of rain. And then the Halloween storm, some of you may remember just from last year, there were 2- and 3-inch rainfall amounts across certainly the coastal zone in Maine. And again, if we look at the historical record, we will see other events like this. It's just that they're happening more frequently now. Summer, March 2012. It's been about 10 years now. It got into the low 80s in parts of the state, including Farmington, or on that day, I happened to be giving a talk on ice ages that day. So I shifted my talk a little bit, but this is my son, my firstborn son at the time. I took that picture thinking, man, when I was a kid, there was always snow in the first part of March. At least, there may have been a couple of years where it wasn't much, but bare ground was much less common back then. And then to wrap this up, I just wanted to say a couple things about sea level rise and then about the Maine Climate Council and some really positive action that's taking place here in Maine. As we know, sea level rise is a very important issue in terms of for any community on the coast. As Castine, there may be implications for infrastructure, for flooding, especially nuisance tide flooding, and some parts of the state are more vulnerable than others. But the issue of as sea level continues to rise, some communities will be faced with some difficult, costly choices about how to relocate certain infrastructure, how to make their communities more resilient to sea level rise. And but over the past century, as recorded in Portland, there's been about a 7.5-inch rise in the sea level. And that trend is expected to continue into the future. And now for, I realize this information it's unsettling. We know that the climate's changing. We know that there are significant challenges ahead. But I think we can be feel very good about what's happening in Maine. In addition to citizen groups and action that's being taken on a personal level, there's also the Maine Climate Council that was established in 2019. And Maine has joined the U.S. Climate Alliance, which pledges to make drastic greenhouse gas emissions. But the Climate Council in particular is signed through, is a bipartisan effort to bring together community leaders, scientists, and stakeholders from across the state to take very seriously and address the problem. How do we adapt to climate change? How do we mitigate? And in particular, how do we meet the greenhouse gas emissions goals that have been set out to put us on a much more sustainable future, to do what we can as a state to help ensure that we have a better outcome rather than the worst case outcome. I, for one, remain hopeful. I see that there's very strong positive movement in the correct direction towards tackling this. This is it's an existential threat to humanity if left unchecked. But if we face it head on, meet the challenge, and do everything we can to reduce greenhouse gas emissions to prevent the world from warming beyond what is maintainable for human society, I think we can do it. I remain hopeful. And I am really proud to be part of the Maine Climate Council as I'm serving on the Scientific and Technical Subcommittee. So my role is to provide the climate science, which then helps inform the working groups on energy, transportation, natural working lands, building and infrastructure, coastal and marine environments, and community resilience. So the working groups are all tackling these issues, and in 2020, Maine's 4-year climate action plan, Maine Won't Wait, was released. And so this is a very strong effort by the state of Maine, something that I think we should all be very proud of. Now with that, I'd like to say thank you, and I'll take any questions you might have. Yes?
What are some other effects of season length changing?
Well, one of the impacts that it'll take some time for this to really manifest, but biomes, so forest landscape, it will eventually change. I mean, a forest can survive for a long time, say 100 years or so, but over time as the climate warms, there'll be species competition. And so species that are better adapted for a warmer climate will start to outcompete the trees and plants that are better adapted for a cold climate. So there should be an overall northward progression of, say, spruce and fir will want to migrate more north, and the broadleaf forest will start to come in more. And so that links not just to the warming, but also the change in the length. I mean, for the growing season, effectively, that plants and trees are responding to. And also, in the wintertime, lakes, lake ice cover, especially, we're seeing a trend towards earlier ice out in the spring, but also a much later freeze up in the fall, especially for the southern half of the state. Also the duration of the snow season, which is impacting outdoor recreation. It's impacting snowmobiling, skiing, and also the changes in winter conditions can either be a benefit or a harm to some of the wildlife. Some wildlife will likely benefit from a warmer winter. Deer, for example, will have, fewer mornings that are 20 below is probably welcomed by the deer. And that's one of the things that's really changing is the wintertime temperatures aren't getting 20 degrees below zero as often as they used to, even below zero as often, especially along the coast. I'm sorry, I didn't quite hear.
Continuing future research.
Oh.
Here or places near here, like Maine. Beyond Maine.
Oh, continuing research on.
Climate.
Oh, on climate. Sorry, I thought you said deer. Well, there's yes, future climate research. One of the areas that I'm really interested in is understanding future climate variability and how certain patterns in, say, the wintertime versus spring and summer, how that might shift in a warmer climate. And the frequency of cold waves, for example, how might that change? And but there's research being done. There's intense focus on the Gulf of Maine and its broader linkages to the North Atlantic region, how future conditions and sea surface temperature, and also atmospheric circulation that connects to ocean circulation via the wind, how that will evolve in the coming decades with warming climate. And also in the Arctic, how the Arctic amplification will proceed and when Arctic sea ice is going to disappear in summer. Even out several decades, we still expect there to be Arctic sea ice forming in the wintertime, but eventually, it could be in 10 years, it could be in 20. Eventually, the summer sea ice, there'll be a complete ice out, and then that will be that's thought to be a threshold that could provide further amplification. But so many areas of research.
Great. I think I know we are out of time. I know some students have places to be at 4, so those of you that need to go can do that. Thank you so much, Sean.
Thank you.
That was fantastic. And probably if you want to ask him a question, you can come up and grab his ear before you leave.
Thank you.
Yeah, first year students, see Professor Cleveland.